Hello and welcome to section 11.7, which is on geometric probability, the last section of this chapter. So today's objectives are to calculate the probability that a point falls within an area of a segment and to calculate the probability that a point falls in a particular region in a figure. Right, so the definition of probability is that the probability of an event is a measure of the likelihood that the event will occur. So probability is always going to be between 0 and 1. And you could write it as a fraction, a decimal, or a percentage. So, for example, the probability that I'm going to grow wings and fly away are 0. There's no chance of that. The probability that I will fall asleep today, 1. That's going to happen for sure. So here we have a little, what's it called? Like a little timeline of what's going to happen. If the probability is 0, impossible, me growing wings. If it's a fourth, or 0.25, it's not really likely. If it's a half, it's equally likely to occur, not to occur, and then so on and so forth. If the probability is 1, it's something that's going to happen for sure. So the way that you're going to find probability, for example, so it's basically what you do is it's what you want to happen over the total that's there. So for example, let's say I had a room with 10 children. It's a preschool class or something that's small. 10 children. 3 of them are girls. If I wanted to know what is the probability that if I randomly choose a child in the class, it's a girl, well, I want then on top, if I want to pick a girl, I'm going to put 3 over 10. What would be the probability of choosing a boy randomly? It would be 7 out of 10, a higher probability because there is more boys. Okay, so let's look at example 1, which is our first objective. It's the likelihood of picking a point on from a segment. So find the probability that a point chosen at random on segment PQ is on segment RS. Okay, so if I want to choose a point on RS, I'm going to count how long segment RS is. So from R to S would be 1, 2, 3, 4, 5, and 6. So it's 6 out of, now I have to figure out how long the entire segment that I'm trying to choose from is. It's PQ, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I simplify this, I would get 3 out of 5. Okay? For example 2, we're pretty much doing the same thing, except this time we want to express our answer as a fraction, which I did in example 1, but now we also want to write it as a decimal and a percentage. Notice that the segment that we're picking a point from is the same as the previous example. It's our PQ, just like before. So PQ is still 10. So now if I want to pick a point randomly on RT, notice RT is only 1 unit long, so it's a 1 out of 10 chance that I would randomly pick a point there. That's my fraction. As a decimal, that would be 0.1, and as a percentage, I have a 10% chance of choosing a point on RT if I was picking from PQ. Second part is TS. Now hopefully you see that TS is a lot longer than RT, so my probability should be bigger. Again, PQ is 10 units long. Now I'm going to count how big TS is. It's 1, 2, 3, 4, 5. So as a fraction, I would always want to reduce. We always reduce fractions. It's a half. Writing it as a decimal is 0.5. Writing it as a percentage, we got 50%. Alright, so that shouldn't be too bad. Now we're going to get to the stuff that's a little bit more difficult. Probability when there's shapes. Alright, so I want to find the probability that a point chosen at random falls in the shaded region. So by definition of probability, if I want to find probability of shaded region, I have to find the area of the shaded region over the total area. For these problems, I know students struggle a lot when it's segments like this or shapes like this, where if you look at the shaded region, this isn't anything. It's not a triangle, it's not a square, it's not a trapezoid. It doesn't have a name. So you have to do some subtraction sometimes or addition. Let's figure out what the shaded region really is. I would do the area of the rectangle, but then I don't want certain things, right? I just want those two arced corners. So what I don't want is this semicircle. And if I don't want something, I'm going to subtract it. So area of the semicircle. And then also notice that there's this little rectangle on the bottom. So minus, I don't want that rectangle, so I'm going to subtract the area of the little rectangle. Little rectangle. Right, now I'm going to divide this by the total area. The total shape is this big rectangle. So area of the big rectangle. So now off to the side, let's go find all of these that I put into this fraction here. The area of the big rectangle is 10 times 7. Length times width, so it's 70. The area of the semicircle is going to be pi r squared. So if this segment down here is 10, and my circle starts in the middle here, the radius of my circle has to be half of that, so it's going to be 5. So it's pi times 5 squared, and because it's a semicircle, I divide by 2. This is going to give me 25 pi over 2, that's 12.5 pi. Alright, so now the last thing I have to find is the area of the little rectangle. Rectangle. So this piece down here, I know its length is 10. It's the same as the entire big rectangle. I need to find this width over here. Well, let's consider this circle and its radius. If I take this radius and I move it and put it up, it's still going to be the same length. It's 5. So from this point to this point is 5, right? That's the radius of the circle. So what has to remain for the width of the little guy is 2. So the area of the little rectangle is going to equal its base, or its length times its width. So 10 times 2, giving me 20. All right, so I have found values for all of these things that I wrote originally here in my fraction. The area of the rectangle, 70. Minus the area of the semicircle is 12.5 pi. Minus the area of the little rectangle, which I found in purple, is 20. Divided by the area of the big rectangle, the total area is the big rectangle, it's still 70. If I use my calculator to calculate this, it's 0.153, which is, whoops, I shouldn't have done that, which is equal to 15.3%. Hopefully you do notice that the shaded region is a very small portion of the whole shape, so the probability shouldn't be very great. It should be pretty unlikely for you to randomly pick a point in this shape within this huge rectangle. Well, it's not huge, 10 by 7, but if you were to randomly pick a point in that rectangle, chances of you putting your finger in on the shaded region, not as high as it would be in the unshaded region. For example 4 here, we again want to find the probability that a point random is going to fall in the shaded region. So because we want the probability of the point being in the shaded region, we have to find the area of the shaded region and divide that by the total area. So whenever you do this and you want to find the area of the shaded region, you have to ask yourself, does this shaded region have a name? Meaning, is it a triangle? Is it a square? Is it a hexagon? Whatever. Notice that this shaded region here is like a little piece of the circle. This piece of the circle is not a sector. The sector would be an entire slice of pizza, but it's the bottom piece of that slice of pizza. So hopefully you guys see that it's a piece of a slice, piece of a sector. It's not the entire sector, but it is part of it. So what you're going to do is find the area of the sector and then take away from that, subtract the area that you don't want. So hopefully you see also that you don't want the triangle piece. Okay, you want the entire sector except for that triangle piece, and then we're going to divide that by the area of the total shape, and the total shape is a circle. So let's go ahead and find all of those pieces. First one I'm going to do is find the area of the sector, and so the area of the sector, to do that, remember we have to set up a proportion. This is from a few sections ago, where the left side is the degrees, the right side is the areas. In the numerators we put degree measures, and in the in the numerators we put the pieces, and in the bottom we put the entire circle. So left side is degree measures. The sector has a central angle of 90 degrees over entire circle, which is 360, equals the area of the sector. We don't know that. That's what we're looking for. And then the area of the circle. To find the area of a circle, you need to have that circle's diameter. Notice that we do have a length given here. We have that this is 8. This is not the radius of the circle because that segment doesn't go all the way to the edge of the circle. This right here, this segment, or the other one below that's in purple now, that's the radius. So we have to find in this triangle the hypotenuse of this little right triangle, the hypotenuse of it. We have the leg is 8, and hopefully you remember that if the central angle here is 90, it gets split in half, so this angle within this little top right triangle is 45. So we do have a 45, 45, 90. The legs here are congruent, so this is 8, this is 8, and the hypotenuse in a 45, 45, 90 is the leg, so 8 times the square root of 2. That then is the radius of this circle, is 8 square roots of 2. So I go and I plug that in for the area of a circle, which is pi r squared. So I'm going to take 8 square roots of 2, square it, and then multiply by pi. As always, we're going to cross multiply and solve for x. So I get 360x equals 90 times 8 square roots of 2 squared times pi. If you type this into your calculator, please make sure that you put 8 square roots of 2, put that in parentheses, otherwise your calculator is not going to square all of it, it's only going to square the square root of 2. And if you do that, you should get 11,520 pi. If you need to, please pause this video and make sure that you get 11,520 when you multiply 8 square roots of 2 squared times 90. Let's divide by 360. And we get the area of the sector, which is 100.52. Again, if you need to, please pause this. Make sure that you do know how to get that answer. All right, so we got the area of the sector. Next, we need to find the area of the triangle. Our area of a triangle is 1/2 the base times the height. We have the height of the triangle. It's 8 right here. Let me do this in a different color because I haven't drawn on this enough, but that's 8. So we have the height. We need the base, this entire length here. And again, this segment is 8, so this segment is 8. So the base is 16. And again, you know, this triangle is rotated, but the base would be 16. The height is 8. So 1/2 times 16 times 8. 2 goes into 16 8 times. So the area here is 8 times 8, giving me 64. Okay, so we found this one. Now we have to find the area of the circle, which we already knew from here is 8 square roots of 2 squared pi r squared. This gives me a grand total area of 128 pi. Again, make sure you square or put parentheses around the 8 and the square root of 2 when you put that in your calculator, or you could just think it's 8 squared and then times the square root of 2 squared, so it's 64 times 2, giving me 128 pi. Now I've found all pieces to find this fraction to figure out the probability of falling in the shaded region. So the area of the sector was what I found here. It's 100.52 minus the area of the triangle, which I found here is 64, and then I divide it by the area of the entire circle, which is 128 pi. If I take my calculator and divide that, make sure some of your calculators will automatically put this in as a fraction, some don't, so you do have to put the parentheses around the 128 and the pi, and we get an answer of 0.091, which as a percentage, if I move the decimal over twice, is 9.1%. Now it should make sense that that probability is very low because compared to the whole shape, that shaded region is very small. Okay, so example 5, again, we are finding the probability that a point chosen at random falls in this shaded region. I'm going to want you guys to try this or finish it off on your own, but I will start you off. So again, if it's in the shaded region, that's the probability we want. We have to find the area of the shaded region over the area of the total shape. All right, looking at the shaded region, I would not be able to call that anything that's not a specific shape. So that means I'm going to have to take something and subtract something else from it. So we are going to find the area of the circle and then subtract from that the area inside. We don't want the white piece. It's like we want to punch that out, and that is a hexagon. And then we divide that by the whole area, which is the area of the circle. Okay, looking at this, we have the radius of the circle, so that's good. So these two pieces, the area of the circle, should be pretty easy to find. Area of a hexagon, you have to do what we've been doing for the last 2 days, which is find the area of a regular polygon. Remember that the way to do that is you have to split this hexagon into these little right triangles, and you have to find the area of that triangle and then multiply by 12. So again, you're going to need to find the base here and the height here. How do you do that? Find this top angle by doing 360 divided by 12. If you get 30 degrees or 60 degrees, you could use special right triangles. Also, if you get 45 degrees, you could use special right triangles. If not, you have to do trig. All right, so that is something that I want you to try on your own, and I will be checking tomorrow. All right, thank you so much. Bye.